Mathletes, we're looking at the laws of probability. There's a set of 4 of them from your formula booklet that you can use, but I want to show you where they come from so that they make a little more sense. I think that you probably don't need to memorize them if you, or even use the formula booklet because they do make sense, but let's try them out. So we looked before yesterday, last lesson, that mutually exclusive events or disjoint events are the ones that don't overlap. And so this piece, this mutually exclusive event, if we want the the union, I want either A to happen or B to happen or both. There's no both, right? So in a mutually exclusive event, so rolling an even and rolling an odd, you either get evens or you get odds, vice versa. And so the probability of even union odd in this is the probability of even or and or an odd. There's no numbers that are even and odd, so it's just the probability of this plus the probability of this. So it's just half plus a half, which is 1, which makes sense. Like, what's the probability that you roll an even number or an odd number? 100% of the time, right? Okay, so that's that first, or that's one of them. Another one that they write down is this, and I think it makes sense because if you want the union of two things happening, the union is this. Yeah, is the probability of tennis or hockey or both. If we want the probability of that to happen, then we need to take the probability of, let's call this, I want the probability of tennis or hockey for this same situation we used in the last video. Here's the probability of tennis, right? So you got probability of tennis, and then also you'd have the probability of hockey. So here's the probability of hockey, right? Probability of hockey. So you'd say, if you just did this numerically, you could do it by number. You'd say this plus this would be here. This plus this would be here. But we've double counted this component. So we have to subtract the overlap once. So let's subtract probability of hockey and tennis. Oh, upside down. Probability of hockey and tennis. Cool. So that's what that means. So probability of one plus the probability of the other minus what you've double counted, essentially. Okay. So that's this one. We got combined events. In conditional probability, you need to have one thing given that a second one has occurred. So conditional probability is A given B. A given B. It means that I know that B has already happened, and so let's figure out the probability that I know that's happened and I want something else to happen. So here's a scenario. You have blue and red marbles in a bag, and you can pull one out, discard it, pull one out, discard it. So your probability changes, yada, yada, yada. We're calling probability of blue, just to help illustrate this, let's call probability, we want B to happen. Let's call that, I know it's out of alphabetical order, but let's call that the probability of pulling a blue on the first pull, getting a blue, right? So this is probability of blue. Then this, because our probability of change has changed, getting a blue again on the second pull would be probability of A. So this is, I want A to happen. I want the second pull marble to be blue, given that the first marble was blue, given that B already happened, that the first marble was blue. And I know that like the syntax is a little fussy with that, but it makes sense that if you want this and this to both happen, I want probability of A occurring and probability of B occurring. A is blue on the second, B is blue on the first. Like, I want blue and blue. I want this and this to happen, right? A and B intersection. First I need blue to happen, and then I need to multiply by the probability that A happens, but given that blue happens, because we change the probability a little bit. So this is doing the same thing that we've been doing, just find the probability here, find the probability here, multiply along the branches. It's in a weird format of how they talk about it, because this one, the probability has changed given that this has already happened. So I want blue again on the second pull, but I have to take into account that that B has occurred, B being the blue on the first pull, and it's messed with my probability. It's a little bit hard to visualize. So this is the equation that they quote to you, which I don't always love, but I take this and multiply out from underneath. So this is this one. Right? This is just, they've divided, because they've tried to leave this by itself, so they've divided this by PA. And so that's what this is. Right? Okay, so let's try it. Let's use it. So here's our conditional. I want A to happen given that I already know B happens. You can take the intersection, I want both of them to happen, and divide by B. And it's delicate about which one B is. So let's try that out. So let's try it again with the hockey, tennis players, even though maybe hockey players get a bad rap. Cup to potato. So let's find this. We've already done this one. Find the probability that they play both sports given that they play hockey. Well, we said we invited all the hockey players in, which was 53, and we said, hey, raise your hand if you're a tennis player, and 27 raised their hands. And so we got that probability. Let's try to get that using this so we don't have to draw a stupid Venn diagram. Okay. So let me just write this down again. I want the probability of A given that B. So this given part is the hardest piece. I need to figure out what is the given. So I want probability of A given B. Oh, well, given is given that they're a hockey player. So this is, I want the probability of both given that they're hockey players. Right? Okay, so now, if you get your head out of the way, Gorkevich. Whoa, welcome to my background. There. Now if we set this up in accordance, we can say this is going to be the probability that both are happening, that they play both sports and they play hockey. These are the only people that play both sports and play hockey, so that's still 27. And also divide by the probability of B. B is the second one. It's the thing that's given. It's the hockey. Oh, these people play hockey. It's 53. We get the same probability that we got before, and maybe we don't have to analyze as much. Let's try that out in an example. So we've got 40 students, and some like these different fruits or dislike them. Now, you notice that this and this and this are more than 40, and it's because some people aren't so particularly that they only like one kind of fruit, right? So first we have to put this all together, and then we'll do some probability with it. So I see that there's 34 who like bananas. This monkey has mad carrying skills. I don't know. Don't ask. Let me make this a little bit bigger so you can see it. There we go. Okay, so there's a group of students. 34 like bananas. That's these people. Don't make the mistake of thinking it's just A. A isn't 34. A plus B is 34. And 22 like bananas. It's not just C, it's B and C. And 2 dislike both fruits. So that's this one. That one's pretty easy. So therefore, if 2 dislike fruits, I know that there are 38 in total that I'm supposed to be looking for. And if I add these up, I don't get 38. I get 56, which is more than 50 than 38. How much more? Well, subtract. You get 16 more, right? I see that there's 56 accounted for here and here. I'm only supposed to have 38. If you subtract them, you get 16. Where'd those 16 extra come from? Sorry, 18. What's wrong with you, Gorkevich? 18 extra come from? They were double counted, right? So the 18 are the double counted. I'm kind of cruising through this fast because I think you're good with it. So these are 18. Now you can work backwards. If you know that if you know that this is supposed to be 34, then you can subtract the 18 and get 16. 16, 34. That makes sense. And then this one is supposed to be pineapple. It's supposed to be 22 people. I've already got 18 there, so there must be 4 here. Add them all up and see if you get those 40 back. This plus this plus this plus this, does that equal 40? Yeah. 4 and the 16 is 20, 18 and the 2 is 20, so now you got 40. Okay, we've set out the Venn diagram. So now let's get to some probability. What's in here? Oh, thank you. I probably could have just uncovered that. Either way, you should be able to build these from this information like this. All right, so like the probability that they like both fruits, not a big deal. It's 18 out of the total, right? 18 out of the 40. Probability that like at least one fruit, it's these 3 out of the total. Right, so 34, right? 40, not 2. You can also say 1 minus 2 over 40, which is 38 over 40. That's fine too. And now we get to the conditional, the moment we've all been waiting for. I want the probability that they like bananas given that they like pineapple. So you bring all the pineapple enthusiasts in. The 22 pineapple enthusiasts come in. You say, raise your hand if you also like, oh, sorry, bananas. Raise your hand if you also like bananas. And so 18 of those 22 raise their hand, and then you simplify. Yeah? And then same thing, you say, what's the probability that they don't like pineapple given that they like bananas? And you say, okay, these are the ones that like bananas. This is given that they like bananas, right? So this is the probability that they like bananas. And let's see, probability of not pineapple. So these people like pineapple. So we want the only banana enthusiasts. So you want 16 out of the total 34 is 16 and 18 added up. Simplify. If you wanted to do this with the equation, I would set it up like this and say, oh, okay, I want the probability of banana given pineapple. So therefore, I need the probability of banana and pineapple over the probability of the second one, which is pineapple, probability of pineapple. Right? And you'd say, oh, probability of pineapple is, back here. Probability of pineapple is 22. And the probability of both is the 18. Right? You get the same equation. So now we have success with those, conditional probability, got it. Last one is independent events. And independent events look like this. If you take the probability of B given A, and that's the same probability as like B given not A, then B doesn't care if A happened, right? So like flipping a coin and then like flipping coin A and flipping coin B. Coin B doesn't care if coin A has flipped or not. They don't like feel each other, some mysterious force. So probability of A happening given B happening given A and B happening given that A didn't happen. If those are the same, then B we say is independent of A. Like I don't care if A happened or didn't happen. These probabilities are the same as just regular B, like not involved with A. That's called an independent event because B doesn't care, right, if A has occurred. Previously, we just saw that the intersection is probability of B given that A happened times A is the intersection. We've been using this as probability of A like that. Probability of A divide, right? These cancel out. We've been using this equation, right? if we multiply the probability b over, you get this equation, which I've now marked up. So one thing that we can do is this we can replace with this if we know it's an independent event. And therefore we can say that if it's an independent event, it follows this rule. If it's an independent event, the probability of both happening is just the probability of one times the probability of the other. Or flip that around, right? It doesn't really matter. And that's a way for us to verify if something is an independent event or not. Independent just means that one outcome doesn't change the next. It's not like pulling out a jelly bean, eating the jelly bean, and now my bag's different. It's flip a coin. The first coin flip and the 100th coin flip don't interact with each other. Or spinning a spinner and rolling a die, they don't interact with each other. And so we can mathematically show things are independent if we can't verify it by seeing it. Right? This is good for looking at like correlation between two things. Like, does vaccination really make your kids have autism? Are they independent or dependent? You can show mathematically that they're independent. Vaccinate your kids. Okay, so let's try this out. So two coins are tossed, and we want to show that these are independent events. Okay. They seem like they should be independent events because one's a coin toss, and the other's the die roll. Okay. So when two coins are tossed, A is the event of getting two heads. When a die is rolled, B is the event of getting a 5 or a 6. Show that they're independent. Okay. So the probability of A is going to be 1 out of 4 because, let's see, we want A to happen. That's 2 heads in a row. So that's half times a half, right? 1 out of 2 times you'll flip heads. You're doing it twice, so that's where the 4th comes from. The event B is getting a 5 or a 6. There's 1 5 and 1 6 on a die, and so when you roll, you have 2 out of 6 chance of getting that. Okay, so what we're ultimately trying to show is that that this is true. We're trying to show that this is happening. So we're going to find probability of A times B, probability of the intersection in 2 different ways, and then show that they're equal. Okay, so if you multiply these together, you get a quarter times a sixth, then you get a 12th. It's 1/4 times a third. Fine. So we have this side. This side is 1/12, and I'm hoping that the other side will be 1/12. So I've got to find this, the intersection, in a different way. So the intersection is heads and heads on one event, and a 5 or 6 on the other side. Now, we have to be able to find this intersection some other way, and so I think they used a graph. You've got to be kidding me right now. So this is a use of these dot probability diagrams. So here's all the things that can happen with the die. Here's all the different ways you can get different heads, tails combinations. And these are, I want 2 heads, so I'm only on this to satisfy, I want A and B to happen. Oh, and I need to get a 5 or a 6. So there's 2 ways to do that, to fulfill both this and this. There's 2. So that's 2 out of the total of 6 by 4. So that's probably where they're getting that 2 out of 24, right? Because there's 24 dots, there's 24 outcomes that could happen. 2 of them are favorable, so 1 out of 12. And so we can say that this is, oh look, 1 out of 12. Also, this side equals this side. It follows this pattern, so they're independent. So that's probability, laws of probability. Many of them make sense, and once you start using them, you'll see some commonalities. They're in your formula booklet if you forget about them, and I always try to multiply this underneath. Like, I like this style better than the way that your formula booklet has it written out. I just think they got lazy and didn't want to write it as a fraction. Not sure though. Hope that helps. We'll see you later. Jump into some practice problems in the laws of probability section. Cool. Bye.